Today we're going to talk about sector area. So with sector area, we need to know three formulas. The first one you should already know. You should know the formula for the area of a circle. The area of a circle is pi times r squared. And it gives us the entire inside space of a circle. We usually write the units, so if it were like inches, we write inches squared, or centimeters, centimeters squared, so I'm just going to put units squared since we don't know what units we're using yet. Sector area is a piece of a circle, like a piece of a pie. We want the inside area of just that slice. So we need to know radius still. And then we also need to know an angle to use the sector area formula. The formula for sector area is theta times pi times r squared over 360. So there's the second formula we need. The third formula is for segment area. If we take our pie slice and we connect a line segment from these points where our pie slice hits, the arc, so the angle hits the arc. The sector area would be, the segment area would be this little space at the top of the ice cream cone type shape. So again, we would still need r and theta for this formula. This formula is a little more confusing. It's r squared over 2 times theta times pi divided by 180 minus sine theta. So those are the three formulas we're going to use today. Area of an entire circle, sector area formula, and segment area formula. They're all for different parts of our circle. So in this example, we want to find the shaded area, so the area of that pie slice. We want to leave our answers in terms of pi. We need to make sure we have pi written in our final answer. And then we're given a circle with an angle and the region that's shaded, and they gave us the diameter this time. So first we have to decide what formula to use, either area of the entire circle, sector area, or segment area. So we look at the type of shape given that's shaded to decide that. So they gave us an entire pie slice, which was sector area. So we're going to use the formula for sector area. We need to identify our theta and our radius in order to use that formula. Theta is easy. The angle for that pie slice is just given to us. Radius, well, they gave us the diameter is 16 inches, but we know the radius is just half the diameter. So now that we have those two pieces, we can go plug this into our formula. Formula was theta times pi, so 42 times pi, times radius squared, so we replace r with 8, over 360. Now I wanted this answer in terms of pi, so pi should never go away. We're going to ignore this. It just comes down for the rest of the problem, but it's not something we're going to put into our calculator. So we're going to multiply 42 times 8 squared, which gives us 2,688 pi over 360. Now we're keeping this exact, pi should always be here, but we should reduce if we can. So we have to ask ourselves, what divides into 2,688 and into 360? Probably going to have to reduce multiple times because I don't know the biggest common factor that would divide into both. I do know they both divide by 2 because they're both even. So I'm going to try 4 and see if maybe 4 works. So I'm going to do 2,688 divided by 4 and 360 divided by 4. Neither of those came out as decimals, so if we divide by 4, we get 672 pi over 90. We're not done yet. Those are still both even, so they'd still both divide by 2. So I'm going to divide by, we could try 4 again, but 90 divided by 4 is 22.5, so it didn't work. So let's stick with 2 for now. 672 divided by 2 is 336 pi. 90 divided by 2 is 45. But we still have to check and see if there's anything else that would simplify. Looks like they'll both divide by 3. So 336 divided by 3 is 112. 45 divided by 3 is not 9, it's 15, sorry. I'm pretty sure that's as simplified as we can go. So this one, it wasn't the plugging into the formula that gave us trouble, it was reducing. There was so much to do to reduce this one. If we had no bigger factors, we could have made that go quicker, but sometimes it's hard to see the factors from the beginning of the problem. So let's try a second example. So this one was pretty straightforward as to how we use the formula. The second example is going to be a little bit harder to figure out what formulas we're going to use. Again, we want to find the area of the shaded region. We want to round our answer to the nearest tenth, but this shape is not one of the formulas we were given. We were given the entire area of a circle, the entire pie slice, or the segment. None of those match what we want. None of those formulas would give us that triangular piece inside. So, thinking of the formulas we have, we know the entire sector area formula. So I could find that entire space in red. But we have something we don't want. We want to get rid of this white area. We don't want this white space. We want just the blue lines. We don't want everything in that red outline. So I could find the entire area, but it gives me too much, and I don't want this extra slice here, this extra kind of crescent moon shape. So if I want to take that away, well, that's our segment area. So our total area of this triangular shape would be the sector area minus the segment area. So they gave us our angle, they gave us our radius, we can just go plug these in now. Sector area is theta, 150, times pi times radius squared, divided by 360. Segment area is radius squared, our radius is 5, divided by 2, times theta times pi, divided by 180, minus the sine of 150 degrees. Now notice, they said round your answer to the nearest tenth. So this time, I don't need to keep it exact, thank goodness. I can just plug this entire thing into a calculator. If you have a graphing calculator, that's a little bit easier. If you have just your cell phone, we're going to have to practice plugging this in tomorrow because it's a lot to try and explain when you're not here in person. So if we plug this in, which is going to take me a second, sorry, this really does take a while to plug in. It said round to the nearest tenth. So we're just going to do one decimal place when it says round to the nearest tenth. So we just have one more example. Okay, our last example is this shape where it's been cut into 8 equal pieces. We're assuming all the angles inside are equal. They want the segment area. My picture is not great, but we're doing the segment area on the circle. And they want 4 different segment areas. So we have 2 problems. There's 4 different areas we'd have to calculate, and they didn't give us any angles. So we have to think back to our information we know on a circle. On a circle, we know the entire circle is considered to be 360 degrees. We also know this was cut into 8 equal pieces. So if we're going to find each individual angle, we can divide 360 by however many pieces it was cut into, 8. So each angle is 45 degrees. Well, I can find that segment area pretty easy for that one piece. I can find one segment area by plugging it into the formula. Our formula said r squared, so 14 squared, over 2 times theta, 45, times pi over 180, minus sine of theta, so sine of 45. Again, we would just plug this into a calculator to get the decimal. We get 7.7. That's just one segment area. We want all 4 segment areas. Well, if they're all the same, this was cut into equal pieces, so they'd all have the same angle and the same radius. And we have 4 of the same thing. We can just multiply 4 times 7.7 to get the total area. We do 4 times our 7.7. We get 30.7. And I forgot to put the units on the other ones, but we'd say inches squared. So we had 3 different formulas: area of a circle, sector area, and segment area. But you can ask these questions where you have to kind of think logically, how can I use those 3 formulas I know to find the area they want me to find? Sometimes we might have to do subtraction, sometimes we might have to do addition. This particular problem we had to divide into equal pieces. So we do have to use some logic on these problems as we go through. Well, I will see you guys tomorrow.